Lasers produce a unique kind of electromagnetic energy, an intense, powerful light not found in nature. To understand how lasers work, you need to know some of the characteristics of electromagnetic energy. Let's start with the properties of one of the most common forms of electromagnetic energy, visible light. When an electrical current is sent through the filament of an incandescent bulb, the current energizes or excites some of the atoms in the filament. The excited atoms give off photons, the smallest amount of electromagnetic energy, in the form of waves. As light waves travel forward, their electric and magnetic components vibrate in two directions. The distance that a wave travels during the time it takes to vibrate one complete cycle defines its wavelength. Wavelengths are extremely small, millionths, sometimes billionths of a meter. When we speak of wavelengths, we use the terms micrometers and nanometers. 1/1,000,000th of a meter is a micrometer, also called a micron. 1/1000,000th of a meter is a nanometer. The excited atoms in the bulb's filament randomly give off electromagnetic waves. Waves in the range of 400 to 700 nanometers are processed by the eye and brain as visible light. Visible light is made up of a variety of colors or wavelengths. Visible light occupies only one small part of the electromagnetic spectrum. As we move out toward either end of the spectrum, the light becomes invisible. On the shorter wavelength side of the spectrum, we first encounter ultraviolet light. On the longer side, infrared. The first characteristic of ordinary light is that it contains a wide variety of wavelengths, some visible, some invisible. It is polychromatic, composed of many colors. Second, its waves radiate in all directions. And third, the light has many different wavelengths, and they're out of step or incoherent. That's why a 100-watt bulb isn't a very powerful source of light energy. Now, energy is the capacity for doing work. It's usually measured in joules. For example, a 100-watt light bulb uses 100 joules of energy every second. And 1 joule of light energy will raise the temperature of a gram of water about 1/4 of a degree Celsius or 1/2 a degree Fahrenheit. Power is the rate at which work is done, and it's usually measured in watts. Here's the relationship between a unit of power, a watt, and a unit of energy, a joule. A watt is work being done at the rate of 1 joule per second. There may be a large amount of energy in the form of electricity going into the filament of this bulb, but the power it releases in the form of light is hardly impressive. Instead, it produces a large amount of heat. Likewise, because the filament radiates light in all directions, its power quickly dissipates as you move away from the bulb. In other words, its power density, called irradiance, is low. But if we concentrate that same power on a very small area, we produce higher irradiance. Now you have some understanding of the properties of ordinary light. But laser light is far from ordinary. What makes laser light, or laser radiation, so extraordinary? Let's take a look at its properties. Laser radiation is monochromatic. All of its waves have the same wavelength, and for that reason, the same color. The wavelength produced by any one laser depends on the material that is energized or excited. The light from a helium neon laser is red. The light from an argon laser is green. And a helium cadmium laser, blue. In addition to light from the visible portion of the electromagnetic spectrum, some lasers can also produce radiation that is invisible, both ultraviolet and infrared. Ultraviolet radiation produces suntan and sunburn. Infrared radiation produces heat. Laser radiation is directional. It travels in a very straight line, even over long distances. Laser radiation is coherent. Its waves travel in the same direction and have the same wavelength. They move in step with each other, adding their energy together. A typical laser beam concentrates its power on a very small area. The result is high irradiance. Divergence is the regular spread of light. As regular light moves away from its source, it spreads out. But with a laser beam, the spread is minimal, resulting in low divergence. These 5 properties make laser radiation so extraordinary. A laser takes energy from one source, for example electricity, light, or heat, and converts it into its own unique kind of light energy. A simple laser consists of a lasing medium, an excitation system, and an optical resonator. The lasing medium can be solid, liquid, gas, or a semiconductor. It's the substance that we energize or excite in order to get its electrons to emit light in discrete packets called photons. Some examples of lasing mediums are solid ruby, carbon dioxide, and nitrogen gases. We use an excitation system to pump energy in the form of electricity or light into the lasing medium. When the atoms in the lasing medium are excited, many of their electrons jump to higher energy levels. As those electrons return to a lower energy level, they can emit photons. Many of those photons, in turn, strike electrons that have also been excited. These collisions cause other electrons to drop to lower energy states, emitting more photons, and the process continues, a chain reaction. Many of the photons travel along the optical axis of the lasing medium. They would escape at both ends were it not for the 3rd basic component of a laser, its optical resonator. An optical resonator consists of 2 mirrors placed in exact parallel to each other and perpendicular to the optical axis of the laser. Some of the photons traveling along the optical axis of the lasing medium strike the mirrors and are reflected back. The reflected photons strike other excited electrons, causing them to emit even more photons. Because they are the same wavelength, traveling in the same direction, the photons add their energy together. The energy of the light wave is amplified, and the result is the intense light of the laser. In order for that light to escape from the lasing medium, one of the mirrors is made partially transparent. Some lasers are designed to emit a continuous beam of light. These are called continuous wave, or CW lasers. Lasers can also be pulsed. A single pulse is so fast that the human eye cannot react fast enough to avoid it. The acronym LASER neatly sums up the basic physics of how laser light is produced: light amplification by stimulated emission of radiation.